In this video, we'll take a look at Euclid's algorithm and try to build a simpler, more intuitive explanation of it using blocks. But before we go further, there are a few prerequisite concepts you should already have a hold on. For that, I've made this slide, illustrating all the concepts you'll need before getting started. This includes factors, multiples, and even a quick summary of Euclid's algorithm if you're in a hurry.
Now, because this is an elementary concept, chances are you'll encounter it again in later grades with little to no further explanation, just problems to solve down the road. Later on, you'll have to work with this algorithm using polynomials, which is somewhat trickier, so we'll leave that for another day. There are two instinctive methods to determine the greatest common divisor, or GCD, which work well for small numbers, but not so well otherwise. That's typically where we turn to Euclid's algorithm, and you'll soon see why. To start, say we have two numbers we want to find the GCD of, 504 and 318. We divide the larger number by the smaller one. If the smaller number divides the larger one completely with no remainder left, then it's surely the greatest common divisor, or GCD. Otherwise, we take that remainder, or the difference between two, and repeat the division using the previous divisor. At each step, we only care about the remainder. We strip away the multiples and repeat the process on what's left, since whatever divides one quantity evenly will divide the other as well. After repeating this process, we're left with the number 6, which divides the previous remainder completely with no remainder. So 6 is the GCD of these two numbers, and a factor of every block's magnitude. Now, two numbers are fine, but what about a third one? Well, here's a neat trick. If 6 is the GCD of two numbers, it's probably the GCD of all three, so we verify this against the third number the same way. Turns out, not quite. Clearly, the number 2 divides both 6 and 10 exactly, so 2 is our new GCD, since 6 already separates as their GCD. Because of this seamless flexibility, you can confidently apply this to any number of values. Now, let's look at some everyday problems where this comes in handy. Here's a classic problem. We have two sticks, and we want to cut them into equal parts as if they were one. The algorithm we just learned handles this gracefully, like a piece of cake. Say you have two crowbars, and you want to find a length that's double the length of the first, or double the difference between them. Again, there's much you can think of. These are the daily sales of bouquets per customer. What does one bouquet cost? Clearly, the price of a single bouquet must divide evenly into each. So the GCD of all these sales figures gives us the price of one bouquet. Last but not least, I have this rectangular frame, and I want to know the side length of the largest square that could fit inside it with no space left over. We use the same approach here, and what we end up with is this grand palace window. These are just a handful of examples, but you can find plenty more in the book. Or better yet, let it find you. I'll leave a link to the book in the description.